In this video, we present a material point method for snow avalanche simulation using large strain elastoplasticity. Slab avalanches are responsible for most of the damage and fatalities related to avalanche activity. A slab avalanche is a complex and multi-scale fracture mechanical problem. It starts with some damage in a weak snow layer buried below a cohesive snow slab. The microstructural damage can lead to the formation of a crack in the weak layer. The onset of crack propagation occurs if a critical crack length is exceeded, leading to dynamic crack propagation across the slope and eventually to the release and flow of the slab. In this sequence of fractures, it was shown that the volumetric collapse of the weak layer during crack propagation was a very important process which explains observations of remote avalanche triggering from flat terrain. NPM is a continuum and hybrid Herwjnen-Lagrangian method, which has the major advantage of dissociating Lagrangian material particles and Herwjnen calculation points. This makes NPM ideal to simulate large-strain processes involving fractures, collisions, and solid-free transitions such as snow avalanches. In NPM, particles store position, velocity, and deformation gradient. First, mass and velocity are transferred to the grid, which allows to compute grid forces and then explicitly update grid velocities. Then, a trial elastic deformation gradient is computed. If the stress state violates the yield condition, the deformation gradient is updated using the return mapping algorithm. Finally, we update particle velocities and positions. We use a modified Gaume yield surface, which allows to reproduce the mixed mode fail behavior of snow observed in laboratory experiments. The parameters of the yield surface are the compressive strength P0, the tensile strength beta P0, and the slope of the critical state line M. The hardening of the slab is performed by expanding the yield surface under compression, which promotes compaction, and by shrinking the yield surface in tension, promoting fracture. This already leads to very realistic snow behaviors. However, it was shown that typical weak snow layers are softening and collapsing under compression. To account for this process, our hardening law involves the norm of the volumetric plastic strain rate, which leads to softening and volume loss under compressive stresses. Once P0 is equal to 0, cohesion is removed, and we use the standard slab hardening rule, leading to a frictional behavior like dry sand. To validate our new approach, we simulate the propagation saw test and compare to field experiments. On flat terrain, we nicely reproduce the observed collapse wave. On a 37-degree slope, we not only reproduce the collapse wave, but also the frictional sliding of the slab. Finally, we can also simulate cases with slab fractures. Moving to the large scale, here is a 2D simulation of remote avalanche triggering. We can also simulate avalanches triggered by explosives. Here is a 3D remote triggering simulation. We tested our model on a bigger slope with spatial variability of snow depths with 30 million particles. Here is the same simulation also showing shear stresses in the weak layer, illustrating anticrack propagation. Our new model allows for the first time to simulate both the release and the flow of avalanches in 3D and at the slope scale using a unified framework.